Hello, today we are going to look at linear, quadratic and cubic patterns. We've already looked at linear patterns in detail, and at the end we're going to have a quick chat about spotting what types of patterns we've got. So to begin with, we're asked to find Tn, so the nth term for this sequence. So what are we going to do? We're going to look for what type of relationship there is between each of the terms. So I can't see immediately, I can't see that I'm multiplying by anything. If I multiply, what do I multiply it to get from 3 to 12? It would be 4, and 4 12s is not 29. So I don't think I'm multiplying by anything. So let's try if we can add stuff on each time. So if we add, what do we have to add to get from 3 to 12? We have to add 9. To get from 12 to 29, we have to add 17. To get from 29 to 54, we have to add 25. Adding on each time. To get from 54 up to 87, we have to add 33. So this has not resulted in what we would necessarily hope for, or we aren't adding on the same amount each time. But if we remember back to our introduction to quadratic patterns, we know that we keep going and see if the second difference is the same. So this is the first difference, which I'll often call D1. So this is the difference we would have used if it was constant to give us a linear pattern, but we don't get a constant here. This is changing. So let's see if there's a constant difference between the differences to give us the second difference, or D2. So here we are going from 9 to 17, we're adding 8. 17 to 25, we're adding 8. 25 to 33, we are adding 8. So this now is a constant. I'm constantly adding on 8 to the difference. So the second difference, we say, is a constant. Now, what does that tell us? It tells us that we're dealing with a quadratic pattern. If you had got the first difference as a constant, as adding on the same thing each time, then we'd know we were dealing with a linear pattern. If the second difference is constant, that tells us we're dealing with a quadratic pattern, a power of 2. The second difference being constant is for a power of 2, or quadratic. And the third difference being constant, so the difference of the difference of the differences, will be constant for a cubic pattern, and we'll deal with them in time. But what does a quadratic pattern look like in general? Well, we know what a quadratic looks like in general. It's going to be an squared plus bn plus c. This is what a quadratic looks like in general, and we do have to know that by heart. This is what a quadratic pattern or a quadratic function looks like in general. Now there's a rule, and I'm going to try and give you a bit of a justification for why this rule occurs, but there's a rule for finding the value of a, this coefficient of the n squared. If we're looking for Tn, what we're effectively looking for is the value of a, b, and c, and there's a rule that you can remember for getting the value of a with relatively little work, and that is to say that 2 times a is equal to the second difference. Now, why this is, or at least a bit of a hand-wavy justification for why this is, I'm going to give you a little bit later on. But for right now, you need to have this rule memorized, that if the second difference is constant, you have a quadratic pattern, which is going to be in the form an squared plus bn plus c, and you need to know that twice a is going to be equal to the second difference. All of that is memory work that you simply have to have done. So let's apply this. We now know we're looking for the values of a, b, and c in order to get Tn. So we are looking for twice a is going to be equal to the second difference is 8. Dividing both sides by 2. We get that a must be equal to 4. So for very little work, so long as we can do a bit of memorizing, for very little work, we get the value of a. Now, other than that, what type of thing have we got? We have 2 unknowns. Now, if we've got two unknowns or multiple unknowns, we know that we're almost certainly dealing with a simultaneous equation. So what equations can we form in B and C that are going to allow us to find the values of B and C? Well, we know the values of the terms. When n is 1, T1 is 3. When n is 1, our Tn is 3. When n is 2, our Tn is 12. When n is 3, our Tn is 29. So we have 5 equations available to us, 5 different values of n. We only have 2 unknowns, so we only need 2 of these equations. So we're going to use T1 and T2 to get equations in B and C. So we know that T1 is equal to A is 4, so 4 on 1 to b squared plus b on 1 plus c, and we know that the first term is 3. So then we know 4 plus b plus c is equal to 3. Rearrange this into the way that we usually keep simultaneous equations, or linear simultaneous equations anyway, and we end up with b plus c is equal to minus 1. Now, in simultaneous equations, it's important to keep track of things, so I'm going to call that equation 1. Next thing, we have the second term in our pattern is 12, so that's when n is 2, so we have 4 on 2 squared plus b on 2 plus c is equal to, second term is 12. And now we have 2 equations in B and C. So we end up with 16 plus 2b plus c is equal to 12. Rearrange that the same way so that we have B and C on one side and the numbers on the other. This is just a convention to make it comfortable for us to do our simultaneous equations, but it's an important convention so we don't make a mistake. And I'm going to call that equation 2. And now I have 2 equations in B and C. Solving them simultaneously is going to give me the values for B and C. And it's important to always remember, or the other way of interpreting this is, if these were functions, we would be looking for where these 2 lines were intersecting each other, where they were crossing each other if we were dealing with functions. We're not right now, but it's important to always keep that double meaning of a simultaneous equation in mind. Now, let's look at what gives us the easiest solution to our problem. We have equation 2 and equation 1. Which one do I want to subtract from the other? Or what do I need to do? Well, I need to get a plus c and a minus c. I can see that if I take equation 2 and subtract away equation 1, I'm going to get plus b is equal to a number, so I won't have to worry as much about my signs. So when you do simultaneous equations, taking a close look at what the possible ways of taking your equations away from each other is very important. So it makes more sense to take equation 1 away so that I end up with a positive value for b. My c's are going to cancel to 0, and I'm going to end up with a positive b. And if I can spot things like that for simultaneous equations, it's really where I need to be. So I now have equation 2 and minus equation 1, and I'm now going to add those 2 together. And because I've multiplied this by minus 1, I end up with plus c minus c summing to 0. 2b minus b ends up being just b is equal to minus 4 plus 1 is minus 3. So I end up now with an equation only in b, and I now know that b is equal to minus 3. Then I need to go back to one of my original equations. Equation 1 is easier to sub into, so that's the one I'm going to use. And I now know that b is equal to minus 3. So I sub in minus 3 for b. add 3 to both sides, and c is equal to 2. Now I was looking for Tn, an squared plus bn plus c, and I know that a is equal to 4, b is equal to -3, and c is equal to 2. So Tn is equal to 4n squared plus -3n plus 2. Tn is equal to 4n squared minus 3n plus 2. And that was what I was looking for, and I've ended up with my quadratic pattern. Now, the last thing I'm going to do with you is a cubic pattern, and exactly the same type of steps, but for a cubic pattern. But I'm going to take this opportunity to go through the different types of pattern that we can end up with in a patterns type question. So if we have a series of terms, term 1, term 2, term 3, term 4, if we recognize that we ever have a sequence or a series of terms going on like this, we could always be dealing with a pattern. Now, what different types of patterns could we get? Well, if we got the difference between these, that would be D1. If we got the differences of the differences, that would be D2. And if we got the differences of the differences of the differences, and they were constant, that would be D3. So, and we could also have if T2 over T1 is equal to T3 all over T2 is equal to Tn all over Tn minus 1, that would be equal to the common ratio OR. And you could also have a pattern, a recursive pattern of Tn being equal to, for example, so this is just an example, it's not a general example, 2 on Tn minus 1 plus 1. So that would be what a recursive pattern would look like in general. So that's our general setup. If we had D1 equal to a constant, that would be a linear or an arithmetic pattern. So Tn would look like an plus b. So this would be linear or arithmetic. If D2, the second difference, was a constant, then Tn would be a quadratic pattern, an squared plus bn plus c, the type that we just dealt with. If D3 was, if the third difference, the difference of the difference of the differences, was a constant, then we would be dealing with a cubic pattern, an cubed plus bn squared plus cn plus d. We're going to deal with this in the next video. And we know our special rule for our quadratic patterns is that 2a is equal to the second difference. And a connected rule is that 6a for a cubic pattern, 6 times the coefficient of the cubed term, is going to be equal to the third difference. And for our those are our different styles that we can end up with. Now I'm going to give you a very brief justification for these special rules that isn't going to make a massive amount of sense to you right now, but will by the time you are doing your leaving cert. And this is differentiation. So I'm going to write this down for you now. So the kind of justification for the fact that twice the coefficient of n squared is equal to the second difference is that the second derivative of a quadratic is going to end up being 2a. When you've done differentiation, that will make more sense to you. But for right now, if you just keep this note that this is a special case, this is not true in general, that the large scale difference would be equal to the derivative, but it is true in this case, and it can help you remembering these two rules.